Ben, the floor is yours. Ben, you're muted.
All right, guys, just
Yeah.
trying to start up my screen share. Share screen. Okay, can you guys see the lecture slides? Is Zoom working?
Yes.
Okay, so I want this to be interactive. If you guys have any questions, any comments, any concerns, just go ahead and shout out. Oh, is this the wrong version? Hang on one second. No, it's that. Here we go. April 20th, 2020. Here we go, everybody. Generative Adversarial Networks. Really fun topic. I hope you guys enjoy it as much as I do. It's relatively new and kind of fascinating, and I hope you guys think so too. So we'll start with the motivation here, which is, and I'll close these other tabs. We're going to go through kind of what is a GAN, how they work, and what kind of problems they can address. And we're going to talk about how we can actually get them to work when you actually want to build them. And that's what we'll go into over the next 2 lectures. What I kind of do is the first lecture, I will talk about the good stuff about GANs, kind of the fun stuff, how they work, and some of the cool things you use them for. And then we'll talk about some of the optimization issues and the actual practical problems and concerns in the second time. It's just a rough guideline of how we're going to be going through this. So in terms of what they do, GANs, based on just the name, they're generative networks. And as you've talked about generative networks for the last couple lectures, they're used to generate samples. So you can use them for creating images, creating music, creating text. Images have very much been the most successful domain, the most popular domain, but you will see GAN work in many different media. Really, whatever you can put into a network, you can try to model using a GAN. It's much trickier with recurrent things like text, music, and speech, but you can use it in really whatever domain you want. So we're going to look at some of the things that have been made with GANs to get a sense of what they can do. So this is actually the original paper from 2014, which is a pretty long time ago now. And you'll see kind of how much progress has been made. What you see in A is the MNIST data set. That's a pretty popular data set. You guys are probably familiar with it. It's a bunch of images of writing of the digits, and you can use a GAN to try and create new digits that have never been seen before, but are similar to the digits that you trained on. B is, I think, the Celebe data set. It's some just small black and white faces. C is probably CFAR 30, I don't know, one of the CFARs, but in general, this is the type of experiment you'll see where you're trying to reproduce images and compare the images that the system's trained on to images that the system can reproduce from itself, what it's learned. And it's trying to reproduce things like images that are similar to what it's seen before. And that was comparing the first paper to what we have now. So just taking a good look at over the years from 2014 to 2018, it's really just incredible the amount of progress. Just going back to the blurry face from 2014 and just each year what we've seen and the incredible quality of images that we're able to produce right now with deep fakes that are sometimes in the news even you'll see deep fakes. It's this quality of image we can get over here with the most advanced GAN techniques. Another great example is some of these high quality images from big GAN, quote, but it's many different GANs together. And you actually see, I mean, a wolf, mushrooms, dogs, whatever it is. These images were not in the training data set. They are relatively large images. They're not blurry at all. And they're being produced by the network. Just another great example of faces that are we're able to manipulate. So what this example actually shows is that it's not just the ability to reproduce, but it's the ability to understand. And that's why we find generative networks to be so important. So what happens in this example is that they learned a vector which is able to say if someone is happy or fearful or sad, and able to generate new faces conditioned on those emotions. As a result, you're able to not make a GAN that can produce faces and just generate faces. It can manipulate faces. So can make people blonde, change their gender, change their age, change their skin, all types of beautiful, interpretable, and actually very impressive results coming out of the GAN research in the last couple of years. It's just 2017 that these types of models have really taken off. There's also a very cool video of generating new celebrities. And I think this hopefully explains the sense of a latent space. That when you have a latent space, that gives you the ability to walk through the latent space. The terminology that people use is called a manifold. And what you're seeing right now, this is a popular type of video that people will do to show off their neural networks. It's actually really pretty, really cool, fun to watch. But what you'll see is basically walking along the manifold. So you are able to create images, and those images in a latent space are near each other. So you are basically able to create and manipulate and warp images from one to the other while walking through only the space of images that look like something. So these are all, if you were to stop it at any point, you're seeing each of these are different faces. And the ability is to lay out all these faces and walk through the images without showing non-faces. So that is, hopefully you guys can see that image and I didn't mess up the sharing part.
Can you tell us more about walking through a latent space?
Yes, it's actually what you can do it with VAE as well, but the latent space does not look quite as good as it does in the GAN. What the idea is you have a simple space, which is your latent space. And your latent space, you'll say, I want my latent space to be a Gaussian. And I want it to have 3 or 10 dimensions, whatever it is. A very simple example, you'll actually just do 2 dimensions of a latent space. And that means all of your images are laid out on a grid. So the output space, when we talk about the output space of images, what is the dimensionality of the output space of MNIST? Do you guys know?
What is what, 700 and something?
Anyone want to guess what MNIST dimensionality is?
10.
That's the label dimensionality. When we're working on the MNIST images.
Oh, 32 cross 32.
Right. Well, it'll be 27, I think. Am I saying that wrong? It's not 32, but it's 784, I think. It's the square root of 784. I want to say 27, 27. I haven't loaded it for a while though. But yeah, so you'll have these images which are relatively high dimension. It'll be like 700 dimensions for MNIST, and for a face, that face is, I don't know if it says here in these examples how many it is, but let's say it's 128 by 128 by 3 because it's got red, green, and blue, there's a very high dimensional space of images. We map that entire high dimensional space of images to a Gaussian that might be a couple of dimensions, it might be 20 dimensions, it might be 100 dimensions, but it's not going to be thousands of dimensions. That gives us a mapping from something that's very simple to something that's complex. And the reason we call that a manifold is you can imagine all of the faces that you would ever see, all the valid faces, all might be in a 700, a 7,000 dimensional space, whatever we're dealing with, but it doesn't cover that entire space. There are plenty of things you wouldn't see. So you kind of imagine it as a ribbon or a sheet, whatever specific thing you're dealing with, but that you are taking this very simple space, that's your latent space, and it's kind of densely packed and everything's there. All your images are in one big closed convex ball, and then you're mapping it out to whatever weird shape the actual faces might be, and that gives you a way to understand them. So as we'll see later with GANs, is you can actually get some understanding. You guys might remember Word2Vec and some of the famous vector addition examples that people have given for that. I believe you guys covered it. Does that sound familiar to anyone?
Yep.
Yep. Yeah. So when you think about latent space, you're thinking about, oh, the latent space of man and king related to the latent space of queen, things along those lines. That's obviously not something that exists in the raw data, because the letters for man plus the letters for king minus whatever does not mean anything at all. But in the latent space, those types of manipulations actually become meaningful. So if you were to transition from the person on the top to the person on the bottom in the space of images, that would just be a linear interpolation from one face to the other face. It's fade one face in, fade another face out. That's what it would look like. You could imagine that. That's not the same as going through the latent space, where on that path, everything is a face. So really what that's trying to say is that when you have a generative model, yes, that means you can generate things, but it also means that you can generate things by mapping them from a simple distribution to the complex target space that you want to have. And that shows some level of understanding of what that space looks like. And it requires some ability to manipulate features and understand what those features are. So when people talk about GANs, for example, they'll use words like unsupervised feature learning. One of the big papers is, I think, just called unsupervised feature representation or something along those lines, adversarial feature representation, things like those. And that's trying to capture that it's not just generating, which might be one of the end goals you have, but it's understanding, and those features can then be used for whatever. It's the amount of understanding you have to have of MNIST to give it a label versus the amount of understanding you have to be able to recreate images with those labels is much greater. And that's why in some ways it could be argued that generative models are a deeper understanding, but that also means that generative models need more data, because the problem of reproducing digits is much harder than the problem of labeling digits. But because it's much harder, it might show more of an understanding. It might develop deeper representations, whatever that might be. And that's kind of what we're getting into here. So the celebrity videos, or the videos of celebrity faces, show you these latent spaces and the way that it's generated. So we'll get into how the actual generation happens in a second. But just another great example is changing the weather. This is a generative adversarial network that is able to take in a video of one season and output a video of what it would look like if it was summer and that same thing happened. So this is the ability to generate completely new images that it's never seen before that are relatively sharp, not blurry. And the reason I keep saying that is because I'll relate to VAEs and how blurriness works. Sorry, got to scroll back and forth. So that's kind of what we can do with GANs. But what we were getting into earlier from that actually was a great question, by the way, of what that latent space is. Because I think if you guys can, if you guys space out on some of the math and some of the examples, but just really understand what manifold latent space, the mapping back and forth, how encoders and decoders work, that would be super helpful. So we're talking about generative networks, and you guys have talked about that before a little bit. But discriminative networks are when you're trying to just predict a label, relatively straightforward. Generative networks, you're trying to generate samples from a distribution, but you can use them for a lot of the same purposes. So it requires understanding the joint distribution. And I guess I got to these slides a little bit earlier with that question. But it's, in a sense, it's a deeper understanding to be able to model the joint distribution of X and Y instead of just being able to model X given Y or Y given X. If you have that joint distribution, you can recover the conditional distributions from a joint distribution. But from a conditional distribution, you cannot recover that joint distribution. And that's maybe a more technical way of looking at what I was trying to say abstractly about one being harder than the other. But the number of variables and the complexity of the joint distribution of X and Y, of generating X and Y pairs, is much higher than a function that just predicts Y given X, or a function that predicts X given Y. And you can also just think of that in terms of mathematically, if I gave you P, X, and Y, you could calculate a formula for P of X given Y, correct? That would be Px of Y divided by the sum over different Ys. You can calculate and recover. It might be hard to recover, but the information is there in the generative distribution. Versus in the discriminative distribution, you're not modeling that entirety of data. That's why it's harder. That's why it might require more data or less data. It's not exactly clear, but its biases may be better. And that's kind of an ongoing argument of when generative networks are better or worse. So there is a kind of traditional viewpoint. And by traditional, I'm saying 95, which is kind of ancient history in machine learning terms. And sometimes it is good advice. The advice goes, when solving a problem of interest, do not try to solve a more general problem as an intermediate step. Try to get the answer that you really need, but not a more general one. And this is often referred to as a reason for kind of keeping it simple in neural networks and trying to go end to end and trying maybe not to do the generative models because they involve solving a larger problem and then pulling out the minor solution out of it. However, still not the most recent quote, but a slight update. It has been argued kind of that the generative models have better biases. That if you had an infinite amount of data and you were trying to generate, or you were trying to identify images, and if you were trying to identify images as 1 through 10, you had an infinite amount of data, you would just train a network that goes from images to what number it is, and you would train it and you would be fine. And that's the easy way to take care of it. However, when you're dealing with a limited data domain, the generative model does tend to actually learn something different than the discriminative network would have learned. And fully exploring that is where really all the research has been going since, especially since GANs came out 5 years ago or so. The other thing to keep in mind about GANs is we're talking about explicit versus implicit. So what kind of model do you think a GAN is? Is it an explicit probability distribution or an implicit probability distribution?
Anyone? It's clearly an implicit one, so I'm guessing.
We'll pause here until someone guesses. It's going to be a long class.
Yeah.
Implicit, I think.
Right. So what this is saying is it's a generative model. It's trying to understand a distribution by being able to create samples from that distribution. And you should contrast that with an explicit distribution. An explicit distribution might be something like, I learned a multinomial. I learned a Gaussian. I have a Gaussian. I can pick a point on that Gaussian and I can tell you what the probability of that point is. I can also sample from it, but the thing I'm learning is an explicit representation of what is the probability of everything in my model. If I have a implicit model, like a GAN, what I can do is I can generate samples from a distribution. I have a model where I can put in random noise, which is my latent space. This is just like a VAE, and we'll get deeper into details about how it's like a VAE. But you put data in, you put random noise in, and you're able to generate samples of faces. That is very different than being able to tell you probability of one specific face. So explicit can, in a sense, be harder. And the reason explicit is harder, I don't know if anyone can guess a good reason why explicit might be harder. There is one thing that's very hard to calculate. It's two words. Normally, I would say they start with an N and a C. There's a very hard to calculate thing in statistics that everyone complains about when they have to calculate it. Does anyone know what that is?
Anybody?
Anybody? I'm having fun asking you guys questions, seeing who's awake.
I don't know. So let me pull someone up. So let me take Pat. Can you answer that?
I don't know how it relates here, but maybe normalized cross correlation.
Normalization is the word you needed.
Oh, no.
Normalization constants are so hard to calculate on any complicated distribution. If you take a high stat class, you will learn how to calculate them for different distributions, but it's only for things that we can really understand. And getting a normalization constant for some arbitrary space is impossible, really. We can tell that maybe one thing is more likely than another, and we can train a model to learn that one face is more likely than another face, but training a model to learn this is the probability of this specific face is very hard, because then you have to have some sense of how many faces there are and integrate a function, and it's very hard to have a normalization constant. But so for example, explicit distribution modeling would be, this is the probability that X is a cat. That's a very simple distribution. That's binomial distribution. Is it a cat or is it not a cat? Binomial distributions we can create explicitly. If you were trying to do an explicit distribution of faces, you would be trying to calculate, this is the probability that this specific picture is a face. And that is very hard to train, because what would you do? You could give a neural network a bunch of faces and ask it to output a 1 or a high number for those faces, but getting all of those numbers to add up to 1 in total is basically an impossible task. Versus implicit distribution modeling is when you're just trying to generate faces and generate labels. It doesn't make sense in the dogs versus cats situation because, well, it's binomial. You can handle that. You don't need to do an implicit distribution. Where implicit distributions are helpful is if the shape of the distribution you don't know, it's not a Gaussian, it's not some easy to understand distribution. So the best you can do is generate from it. So these are not completely separate. It is possible to kind of recover one from the other, but it does take work. You guys can think about what you could do going from one to the other, and actually a couple techniques. And we'll talk about that a little bit later when we're talking about how to evaluate GANs. When you have a explicit distribution and you want to be able to sample from it, let's say I know probabilities of things, but I can't get samples from them. There are techniques that basically are related to Metropolis Hastings, and maybe we'll cover that at some point. There are techniques for creating samples from that. And in terms of going from an implicit distribution to an explicit distribution, all you can do is sample. So basically, if I can generate samples and I want to calculate the probability of something, the best I can do is generate 1 billion samples and then count how many of them were that something. Does that make sense? And that's basically the most naive but straightforward way to be able to use a GAN to calculate the likelihood of something. Because it doesn't give you a likelihood, it just generates samples. You can generate enough samples that you can create an estimate of the likelihood of whatever it is you're looking at, if you need the probability versus just samples. So that was just a rough understanding of what kind of generative networks are and discriminative networks are. But now we'll actually talk about GANs and what they do, because that's, I guess, the part you guys are all interested in, hopefully. They came out in 2014, and the goal is just to create a generative model that you can sample from, and it's done using a pair of adversaries. This is kind of what makes them hard to train, what makes them really interesting and unique, is that there are 2 players in this game. They have to fight each other at the same time, and through the way they interact, they are actually able to solve the problem we want to solve. This rough description, if you guys are familiar with duels, that might light up a few light bulbs. If it doesn't, that's not a problem. If you have extra time, feel free to look that up later. Always an interesting a branch of optimization. So what these two adversaries are, they're always referred to as adversaries, are a generator and a discriminator. And what the two things are, the generator is just like with VAEs. It is a network that outputs your target domain. If you want to create MNIST images, your generator output is MNIST images. The network has an output that is reshaped or whatever into the shape that you want. This creates your target domain. Traditionally, X is your input and output. That's your world space, that's your image space, whatever it is. And Z is your hidden or latent space. Also, in terms of words, sometimes you'll hear it referred to as encoder and decoder. There are plenty of words you can throw around, but it's just like what you used in a VAE, where you would have called it in an autoencoder, this would be called a decoder, but in the case of GANs, we actually call it a generator. What it does is it takes this latent space, this hidden space, the encoding, whatever you want to think of it as, and it goes from this kind of very simple distribution to the complex distribution. The actual design of that, that's CNNs, that's whatever it happens to be for the specific domain. All that matters is you have this network that goes from Z, your latent, to X, the inputs that you're trying to reproduce. This generator function is deterministic. And as you'll see often in machine learning, the way we make something that's stochastic or random is we take a function and we put random noise into it. And that's the easy way to do it. It's a quick hack and it works really well. So we want to have a random function that can randomly create X's, and we can't do random, because nothing is random under the sun. You have to have a random seed, you have to have a random source. We instead just create a function that takes in random and then creates deterministically from that random your images. But what this gives us is the ability to produce images, but we don't know how to train it. We want to train this generator to produce images that look good, but how do you define an image that looks good? You don't know what latent space maps what to output. You don't know how to do this. That's where the discriminator comes in. So we have this generator. What the generator is and what it does should be pretty straightforward, but how to train it is where GANs become complicated. So any questions on what the generator part of the GAN is? And feel free to jump in later if you guys missed. It's no, you know, if you miss a question now, feel free to go back a couple slides if you guys need to. Just let me know. The discriminator is really, you can think of it as your loss function. And this is where neural networks branch off from other networks. Instead of training it with like an L2 loss, you train with a discriminator loss. The discriminator is slightly more complicated, as we'll get to, but the discriminator tries to tell the generator what it should be doing differently. Yes, it learns a loss function, but that loss function cannot be described as just an L2, as an L1, as cross entropy, as any of the other simple losses that you think of, because now this loss function is both very complicated because it's a neural network. It can be so much more complicated than, you know, square everything and sum it. And it can also change over the course of training. So you have this adaptive loss function, this loss function that's implemented by a neural network. And that network is able to guide the generator into what it needs to do. So the back and forth that we see is that the discriminator tries to say, this data is real and this data is generated. And it tries to tell the difference between the two of them. The generator tries to confuse the discriminator so it can't tell the difference. And that is the back and forth. The generator has been described as counterfeiter before, or the faker sometimes, if you want to try to put fun words on it. The discriminator is not a network you want. It's not a network you use. Your goal is not to make the discriminator. The discriminator's goal is to train your generator. So when you train a GAN, you will train a pair of discriminator and generator. When you're done, discriminator is trash. Your generator is the thing that you were trying to make. So that was a bunch of words, but to try to put it into pictures, here's what we're looking at. You put noise into the generator, and the generator is able to transform noise into an image. And you guys can imagine a function that takes in 10 inputs and outputs a 32 by 32 block of colors. Something along those lines. No, it's 28 by 28, isn't it? Yeah, eminence is 2028, 784. Yes, sorry. Anyways, your random noise goes into your generator, it creates an image, and so you have two different types of images. You have images generated by your generator, which are fake, which don't really exist. They're being created by your neural network. And you have your training set of images. And your generator never actually gets to see that training set of images. Your generator is only basing what it produces on the discriminator. So the discriminator tries to tell the difference between these two different sets of images. It's trying to establish a little hyperplane which says that side is real and that side is fake. That's its job. And then the generator just uses that information to say, okay, then I need to go over there so that I look more like the real guys. So the generator is not directly trying to match the training data. It never sees those images. It tries to confuse the discriminator, and the discriminator is what sees the real images and the fake images and compares them. This will hopefully try to make it clear. And I guess when you first see GANs, I'm not sure if it's either they make perfect sense, or they're hard to understand, or they're just kind of like mind-blowing of like, a network that trains a network to do something. That sounds really cool. But here's like a very simple kind of step-by-step. This is a chronology from left to right from actually the original paper. So what we see here, the line at the bottom is your Z. So that's your latent space. You put in that block of data. The function maps that data to X, which is the line above it. And we're trying to train it to learn to map the data to a little normal distribution. So that's why you see the mapping slowly changing from left to right to being towards the center. But those lines aren't really the important part. The important part is the one on top, the black, blue, and green. So what we see is those little black dots are your data. The data doesn't move. That's what you want. You want this little normal distribution. The green line is, let's say that's what your generator is currently doing. So if what your generator is producing is the green line, and what your real data looks like is the black line, then your discriminator, which is the blue line, might do something like that. What that's trying to indicate is your real data is here on the left, your fake data is here on the right, so your discriminator is going to learn a function which says real's over here, fake is over here. So you can see how it learned to create a high value over on the left, where the real data is, and a lower value on the right, where the fake data is. Your generator then used that gradient of which way towards the real data to modify what it was producing and to start producing data that looked better. So in a nutshell, that's trying to visualize what it is to picture in your mind, you're not directly seeing what you want to do, but someone else is telling you, oh, that looks bad, but if you changed this way, it would be better. So that target network you are propagating through the discriminator into the generator. And in this function here, the actual back propagation is going all the way through that entire stack of generator and discriminator. So anyways, in terms of the actual math and how we do this, it's called a min-max game, and here's the original min-max game as it was formulated. Plenty of changes to that, and plenty of modifications, which we're not going to get into right now because we want to understand the original first. But what you're trying to understand is that there's a min-max game, two people playing against each other. In this notation, D and G, as the traditional notation, is discriminator and generator, X and Z being your images or audio or whatever, and Z being your latent space that you're trying to produce from. And to kind of unwrap this statement, what it's trying to say is the game is the thing on the right, and on the left, that min-max is trying to say is the generator wants this to be the lowest value possible, and the discriminator wants this to be the highest value possible. So these two people are fighting over what that value on the right is going to be. One is trying to maximize it, and one is trying to minimize it. And those two different values are, you may or may not be at a point where you can easily recognize this as, oh, that's binary cross entropy, but that's what we're looking at here. But we're basically just looking at maximizing the log likelihoods of each thing. So what we're really looking at is maximizing the discriminator. The discriminator wants to label real as real and fake as fake. And the the generator wants the discriminator to do the opposite of that. So they're pushing in opposite directions. So looking at this function, which might be a bit complicated, we can break it down and see what happens if we actually look at the optimization process. So this is the part where we're going to talk a little bit about math, and this is the part where if you guys feel like you miss a step, definitely jump in. Please don't feel embarrassed. I don't know if there's an anonymous chat feature, but feel free to throw things out there, and I'll try to take it through and not jump too much. So at the top here, we have our function that we're trying to min, max, and fight over. When we look at that function, it's the expectation over x's drawn from the real distribution. That is what the x sim PD kind of notation means. It's what's the expectation over x's drawn from real of this value, and what's the expectation over x's drawn from the generated of this value. So there are two expectations, and what we can do is we can look at those two expectations together, and expectations are just an integration over that space multiplied by the probability. But what we're looking at is each individual x. So what we're trying to say here on this slide, to keep it simple, is that if we're trying to maximize or minimize this top thing here, if we're trying to optimize that at each point, what we really need to maximize is just this. What the slide is saying is that if your discriminator, if your generator is completely free, it's the most complicated network you could ever want. It is completely flexible. It can represent anything. It is really a universal approximator. Then each x, it could output a different value. So if at each x, it's a different value, then we can basically ignore this expectation here and just optimize at each x. So instead of the expectation here over x is drawn from real and x is drawn from fake, what we can look at is the probability that something is real times this, plus the probability that x is fake times this. So we're trying to understand right now if the discriminator is trying to, and if we scroll up, maximize this value. If the discriminator tries to maximize this value, how do we figure out what the discriminator would be? And we can follow our usual process of trying to optimize something and take the derivative and set it equal to 0, because that's how we've been optimizing things since calculus. So step one is working from the inner way out. What is the optimal discriminator? We start from this function that we started off with. We take each point and we set the derivative equal to 0. So hopefully you guys can see how this derivative right here comes from the derivative of this guy with respect to dx. So the derivative of the log is 1 over et cetera, et cetera. We can work through calculus if you guys have questions, but the derivative of this statement here is right here. And once you set that equal to 0 and solve, we end up with this solution down here. And what the solution is saying is, if you were to train your discriminator to get the perfect discriminator, what value would it output for each x? The value that it would output for each x is the probability that x is real divided by the probability that it is fake plus the probability that it is real. That is a ratio. That is something we can learn. So earlier.
So Ben, that looks like the base rule with the equal priors, doesn't it?
Right. You actually jumped ahead to my next question. I was going to ask you guys how you could describe it in words. Like, what does that mean? Like, how would you describe what this is? And yes, it is a ratio. And the reason that it's a ratio is because of that normalization constant we were saying earlier, which is probability that something is real. PD of x, that is so hard to learn. it is so hard to just say, oh, out of all the faces in the world, the likelihood of this specific face was X. For every possible face to have a function that could do that. That's really hard. We're not trying to learn the probability that something is real. We're trying to learn the ratio of the likelihoods that something is real versus something is fake. And that ratio is something that we can learn with a neural network just fine. And that's why we needed to bring this discriminator in there. We couldn't learn just one, just that term by itself. I don't know what that's divided by. I don't know what it's constant up to. But the ratio I can do. I don't know what one likelihood is or the other likelihood is, but I can tell that one thing is more likely than the other. That is easier to learn than the explicit likelihood of something. So you'll often see this in machine learning. You'll see this in advanced stats, where to avoid trying to learn normalization constants, which are really hard to learn, we just work with unnormalized values. We work with ratios. We'll work with other things. We'll work with conditionals sometimes. So this is just a conditional expectation. And you hit on that with the base, that this is a conditional. And I don't know if anyone can explicitly describe what this conditional is in words, or has a good way to say it. But the way I would describe this ratio is, given that something is either sampled from generator or discriminator, what would it look like? I'm sorry, is chat coming up and I'm not looking at it? Oh, sorry, I should have had chat up on my screen. I'm sorry, I'll just go back for a second. How do you know how large the latent space is enough to describe the full space? That is an experimental issue, and that's also how complicated of a representation you want. So if you were to map every single face in the world down to 2 dimensions, that would give you the ability to put everyone in the world into 2 dimensions. Whether that gives you the flexibility to represent all the different math, probably not. So it's like a dimensionality reduction question of, if you do PCA, how much PCA is too much? How many things do you want to drop off? So there's definitely a skill to it. I could just say 42, or like 64 maybe, just based on most papers. But we're, in general, people are looking for something that's in the maybe in the 30s, maybe in the 60s, maybe like 100 or so, but something that could potentially be manageable for someone. And that sounds like a lot of dimensions, but we're talking about faces. If you guys go play a video game and use a profile creator, how many different sliders do people have on setting your forehead and your brow ridge? And as we'll get into later, really trying to break out the latent space and have meaningful representations is a really big part of GAN research. And dx is the output probability the discriminator thinks X is a real input. Yes, exactly. It's the probability that it's a real input given that you are equally sampling from both. And that will come into later. So given that I have a 50-50 shot.
So then I think we lost the last few minutes of you.
Did I cut out, or what happened?
You cut out, at least for me. So can you go back about 3 minutes?
Oh, I was answering some of the questions about from the group chat. I want to be clear. Did we get through the math, or where were you guys? Okay. We were talking about this question. I can hear no problem taking off with me. Oh, by the way, guys, Bix's internet has been known to be a little bit notorious. I'm sure you've noticed. I'm sorry if I dropped off, Bix. I hope that doesn't mess up the recordings, though.
That's okay. That's fine. Keep
continue. Okay. But hopefully everyone's been on track. Anyways, so this is, if you were equally likely, if your prior probability is half of these samples are coming from real, half of them are coming from fake, given that this is your specific example that came out, now what do you think the likelihood is? So it's really posterior given that. So describing in words, you're kind of the words of trying to understand what this value is, but really what your D is telling you is this is more likely to be discriminator, more likely to be This is more likely to be real, more likely to be fake. So just looking at this equation to kind of think of 3 different possibilities. If this image is always, it can only come from your real data, your generator can't produce it, then that would be a 1, because 1 over 0 plus 1 is 1. If it's something that definitely comes from your generator, there's no way it came from your discriminator, it would be a 0 over 1 plus 0, which would be a 0. And if something is equally likely to happen under each of them, and this is really the point we're striving for, if your generator and if your generated data and your real data have the same distribution, and your discriminator can't tell the difference, and the likelihood of an example coming from one versus the other is exactly the same, then 1 over 1 plus 1 gives you a half. So what we have is we will have a half if our model is working correctly. We're done training and everything's working correctly if we have a half, because if your D tells you a half, that means, hey, your neural network cannot tell the difference between real data and fake data, so I guess you're doing as well as you can do. Now, diving a little bit deeper into this equation that we started with, we can plug that discriminator value. So we figured out what is the value of the discriminator when you've trained it. When your discriminator is working correctly, it gives you PD of x over PG plus PD of x. So that's the value we have. We plug that back into our equation. That's going way back. That is this same min-max equation that we have. So now we plug in our value for D. And when we plug in this value for D, we can do a little bit of algebraic manipulation, a little bit of messing around, but we're going to make this, which is kind of ugly, look into a very standard, common, short divergence term, which you guys may or may not have seen before. But the way we're going to do that is we're starting by defining this new distribution M. And M is going to be the average distribution. What this notation is saying right here is it's half real, half fake. M, you create M by adding the real probability and the fake probability and dividing by 2. And what that gives you is the mixture probability of what if there was a half chance of doing one or the half chance of the other. Maybe a better way to think about it is 1/2 of real plus 1/2 of fake is what M is. M is half real and half fake. The way we're going to use M, and M is a distribution, right? Because if you were to take any 2 probability distributions and take their average, you have another probability distribution. If you take half of one distribution, half another distribution, great. That's still a distribution. So it's just a new distribution we're defining. So algebraically, we put that back into our this equation that we have. So you can see PD plus PX is equal to 2M. So we've got that 2M there. And then because this is a log, we can take that and take the negative log out. So instead of log of A times B, or I guess log of A divided by 2, we have log of A minus log of 2. And they come out of that expectation because it's just a constant term. So we start by pulling the 2's out, pull both those 2's out, and that gives us a negative log 4. And when we do that, now these terms right here are really simple. That is a KL divergence because PD of X, that's your real data distribution, and M of X, that's your new average distribution you created. Same thing over here. PG is your generated distribution, and M is that new distribution you created. So when you see something that's expectation of A, log of A over B, that is the KL form. And when you start seeing that kind of like expectation over one log of that thing over something else, or the other way around, you'll eventually learn to just be like, oh, I think I see a KL divergence coming in the future. And that's what that is. So this is just the KL, and that's the KL. So we've got, it's these two different KLs being added together. But there's actually a term for that. So it looks like I made it a little more complicated in this line here, but you'll see why in the next phrase, in the next slide. I don't know if anyone knows the name of that, what that divergence is. This little block right here has a special name in statistics, and that is called the Jenson-Shannon divergence. And what that is it's the divergence from an average. I guess the one other little algebraic thing I should probably point out here is that this thing here, this block was D, and this block is 1 minus D. So you can see how 1 minus D, 1 minus this gives you this. PD becomes the PG instead of writing the 1 minus. Anyways, so here is our JSD. The JSD, it's just a common divergence that's used in statistics. It has a couple nice properties. One useful property, the numerator of MX won't be 1. Oh, because these are both the conditional, and it's really because we can't even calculate MX. So this is the probability. So to imagine what PD of X is, that's the probability under real data of this particular face existing. So that would be like, if I took a picture of your face and we just assumed like all faces exist right now, that would be 1/6 billionth, roughly speaking, if that makes sense. But it's obviously much different than that because there are infinite faces and there will be many more faces and less faces. So that those two things that we're adding there are the likelihood of a face being produced. And they don't add to 1. The ratio up at the top, we're subtracting 1, but it's that we have no way of telling what this distribution is. It's not gonna be 1. It could be anything. God knows what it's gonna be, but it's the the PD of X and PG of X. We're writing this just to say what M is and what we're calculating, but that's kind of what makes the GAN is we are minimizing the divergence with M, and yet we can never know what M is. M is impossible to calculate because M is the likelihood of a face. And that's such a large, complicated problem to, I don't even know how, it's impossible to do the normalization of that. You can do the likelihood of die by counting how many times each die, whatever, however you're doing it, if you're rolling more than one at a time, whatever. But you can take the likelihood, you can take the counts and divide them by how many there were. And that gives you a likelihood of something. You spin something 100 times, you take how many times it landed on here, divided by how many times you spun it, that's the likelihood of this specific thing. We're talking in continuous space, what's the likelihood of a face? We can never make it. And yet, our GAN is able to KL between them. Well, this is kind of what we're saying, is how do you minimize the KL between a distribution you don't know or understand? You have examples from the distribution. These are all actually great questions. Thank you. And this now you guys are starting to click, which is, and hopefully everyone can see the chat, which is we need the intermediate value. Oh, sorry. Why can't we do the KL between PD and PG? when I'm starting to talk about the JSD, it's got a couple issues. One is that KL divergence is asymmetrical. So KL between D and G and G and D are two different numbers. Versus Jensen standard divergence has some of the properties of KL, but it's symmetrical. So you can see in the formula for JSD, if you were to swap A or B, your formula would be the same, versus if you were to have P log P over Q is not the same as Q log Q over P. So we see that the JSD is a little bit more stable. It's not as stable as other options, which we will get to next time. And it's also because we really can't directly calculate either of these. It's not even that we're optimizing the JSD directly. It's that we have this big complicated minimax game, and when we play it, we end up minimizing the KL, or we end up minimizing the JSD. So I think that's what you meant by the intermediate value of having that M. So it's handy for making things more even. Also, JSD never is infinite. It can get really big and get really small, but like it does have some more. So KL can become infinite because it's A over B if B ever becomes 0. Versus when you're doing the Jensen-Shannon, it's always A over the average of A plus B over 2. So you know if A is non-zero, then A plus B over 2 is definitely going to be non-zero. So the KL between A and A plus B over 2, you know that denominator is never going to be 0. But if it was between A and B, it would totally be possible for A to be non-zero and B to be 0, and then suddenly you've got infinite values, and you're probably not optimizing anything great. So it's a little bit better in terms of stability, symmetricity. So what you're trying to do is make the distribution similar. What the GAN is doing in short, what all this is saying is GANs minimize the Jensen-Shannon divergence between the real and generated distributions. You take the real distribution, you take the fake distribution, you try to make them the same, and the thing that you're measuring to try to make them the same is the Jensen-Shannon divergence. It's just that we can't calculate the JSD between two distributions directly, but using a neural network as the intermediary, we can actually calculate it. And that allows us to calculate the divergence. So anyways, it's a little bit more complicated than making two things the same. You're trying to make each one, you're trying to make it more similar to the average. So it's minimizing the average KL between each of them and the average distribution, as opposed to the KL between A and B. So it's the average KL of A and B between the average of A and B. Maybe a little verbose, but that's really what this is trying to say, is the average distribution, the average KL to the average distribution. And that's what JSD is. Always is, in terms of machine learning, it will frequently tend to be better, just in terms of if there's no chance of getting infinite values, then you're probably going to have more stability issues or less stability issues. But practically speaking, most of the time we're using KL divergence as just the go-to. But it's really not a better or worse. It actually comes down to what you're trying to calculate. So if you guys go through the VAE, kind of like the VAE lecture notes or some of the derivations, you'll see that VAEs use a KL divergence in a very specific way. So where KL really starts to make sense is when you start getting into variational inference and figuring out what all that's about, which might not be the, I don't know, if you guys are really excited about variational inference, I can dive into that more. But it's somewhat like the likelihood of estimating one thing under something else KL calculates that very effectively. So KL is good for giving us probabilistic bounds that, like, KL is very useful for upper and lower bounds that are very handy, but in terms of the numbers that come out of it, they can be very wild compared to JSD. Versus in terms of what JSD is, it's harder to describe. It might not have as many probabilistic interpretations for what you're trying to do with it, but numerically speaking, it's not going to give you quite as many nans as you might have gotten otherwise. It might be a little bit smoother. Anyways, so what we see here is that there is a stationary point. We've got these two guys, they're fighting against each other. We went through the optimization. I encourage you guys to kind of just briefly scan through the math again to see if it makes sense to you, but it's one equation, we say min and max. Then we did several slides of how that little min max ends up calculating and minimizing the JSD between real and fake data without ever knowing what the actual probabilities are. So there is a stationary point. It's 0.5 for all inputs. The discriminator is going to output a 0.5. It's a 0.5 because it doesn't know what the difference for anything is. And if the discriminator is outputting a 0.5 for all inputs, then the discriminator is just a flat data, so the generator has no reason to move. And at that point, that is a stationary point. That is a point that something can sit at and not move. But when you think about stationary points, you should think about balancing a pencil on its tip. There is a point at which it can be stationary, but maybe not necessarily stable because things don't push it towards that direction. And the difference between something being stable and not stable is not just whether there's a place where mathematically you can say all the derivatives are 0 and here you are, that will stay in this position if in this position. Stability is a question of whether things will go towards that position or go away from that position. So something with weight at the bottom can stand still, but it's also stable because if you push it a little bit to the side, it's going to fall right back. Versus balancing your pencil, yeah, you can do it, but if you push it slightly to the left, it's going to move further to the left. And if you push it slightly to the right, it's going to move further to the right. So it's anti-stable. And understanding that in GANs, we can prove that there is a stationary point. There is a solution to this game in which you generate the data you want, but you can't prove that you get there. And that's part of the problem with the optimization issues we'll be getting into more next time. I do want to do a quick time check.
We have 12 minutes.
12 minutes, okay. Oh, so there is a stationary point, but whether you get to it or not is not guaranteed. So what we can see is that they actually become unstable, and we're going to talk about the instability next time. But for now, I want to get you guys through the actual, and I think the hard parts of how to train them we can go through next time, but what you can do with them is maybe the exciting part for now. But this is just a preview of it's hard to train and hard to get correct. There's been a lot of research on how to make them more stable than what I showed you in that original formulation. And we'll go through that math part. But when you train a GAN, you can actually get it. They look very weird to train, not like a regular neural network. Not like a regular neural network at all, that when you train, they slowly kind of form out of a mush to end up with the digits that you wanted or with whatever images you wanted. And diagnosing and examining them is very hard, actually. So we were looking at some photos of GANs. And one important takeaway is perceptual loss and perceptual distance. As we talked about ideally, it calculates JSD. Great. Why are we doing all this thing? The other key point is our loss function is being created by a neural network. So we have a neural network that's trying, if there's really one slide I could get you all to understand, would be maybe this one and the implications of it. That your normal loss functions are like a minus b squared and then add them up, et cetera, simple losses. Your loss function is implemented by a neural network. Neural networks are influenced and modeled after perception, and they have so many biases built into them. Neural networks have convolution and invariance and all these things that we do in neural networks. And now we can do that in our loss function. If the thing that's telling us the difference between real and fake has some shift invariance, then we've got a loss function that has some shift invariance. And compare that to, let's say, an autoencoder, and you're training that with an L2. If you move an image 1 pixel to the right or 1 pixel to the left, the L2 difference between each pixel is just huge. There's a huge difference because you're defining things in terms of L2. If you're defining things in terms of how does my neural network see this, and that neural network is built with neural networks and convolution and shift and pooling and whatever else we might have in that neural network, then suddenly our loss function is modeling that too. We're doing a more meaningful loss. We talked a little about implicit distributions. It's hard to train. So the good, the bad, the ugly is beautiful results, kind of unstable theoretical issues, not as theoretically sound as VAEs, but they work and they're beautiful. GAN evaluation, I think we will touch on next time because that kind of goes onto how we get into them. But as I said, they were hard to evaluate. And it's hard to estimate the test set likelihood. It takes a lot of sampling. If you guys do projects with GANs, you'll often see, hey, I made a GAN. I can look at the pictures and give you a thumbs up if I like it. But being able to put hard numbers on GANs has been a hard problem because it's not how many numbers did you get correct, how many things did you identify correctly, it's did you make faces, did those faces look good, which is much more abstract and harder to put into numeric terms. But I think the actual details of the evaluations, because I want you guys to think about some of the differences between the GANs and the VAEs. GANs are noisy and complicated, but they are training exactly what you want to train. What a GAN does when it works correctly is it generates from a distribution. VAEs do a lower bound. They are effective and they are efficient, but their goal isn't to model the problem that you actually want to solve. What the variational and variational autoencoder means is, hey, here's a simplification to it, which is way easier to solve and we could do it quickly. Let's just do that. So VAEs and GANs can be used for very similar things, very similar tasks, and they can be used in combinations. GANs tend to be the ones that are harder to get working, but also the ones that are sharp, versus VAEs tend to be very quick to do, but they're approximating what you want. And you can visually see that as blurriness in your results from VAEs. I'll often find it handy to, when you're dealing with a problem where you might need to do a generative model, start with a VAE, see how well it works, see if it's a little blurry, try again. And like that gives you some flexibility to like work things out. If you can do the VAE, if you're having issues doing the VAE, you're probably gonna have more issues doing the GAN. Get the VAE to work. It might be blurry, but it's guaranteed to train, versus GANs can just run off into chaos and you'll spend years working on hyperparameters, as far as I can tell from some project reports. So be very careful with getting sucked into GANs, and they can be beautiful and amazing, but try the simpler models, build your way up to the GANs, and make sure that you use the more advanced training methods and not the simple formulation I showed you here. Use what I will show you next time if you do want to play with them, because that's way more effective. I'm sorry if that's a little vague, but you'll see the optimization issues next time. This is a little recap on VAEs you guys can read, but hopefully you were all awake during those lectures. Similar ideas, just instead of training on real data, VAE, you put data into the encoder, it goes in, then it goes out into the decoder. With the GAN, you're starting right with the decoder. You're taking random samples and putting them into the decoder during training. So in a GAN, during training, you are generating from random samples, from true random samples from your prior. You are generating it based on the random distribution that you want to be generating from. With the VAE, you're not putting random normal samples into your generator, into your decoder. You're putting whatever you happened to have encoded. And you are trying to make your encoded data as close to the normal distribution as possible. That's what a VAE is let's do an autoencoder, but let's make that middle section, that hidden layer, look as close to Gaussian as we can, versus in the GAN, the middle is just sampled from a Gaussian. So both of them train a generator or a decoder, whichever one you want to call it, but in one of them, the decoder is receiving data that's just been encoded, and in one of them, the decoder is receiving data that's directly being sampled from your prior. So what that means is your GAN is trained and evaluated on the same distribution, versus your VAE is always going to be trained and evaluated on slightly different distributions, which can help explain why it has some blurriness. This is a list of GAN architectures. We're probably not going to cover all of them today. We're definitely not going to cover all of them today, but I will dig through them next time and just give you a brief overview of kind of what they can do. So you've seen GANs as just generating a face, but more than just generating a thing, just looking from the top, you can generate a thing based on something else. You can generate things recurrently. You can use it to do unsupervised learning. Categorical GAN is unsupervised learning. InfoGAN is, I think, one that you guys would find kind of relevant, since you were asking questions about the latent space. So in terms of the latent space, InfoGAN did great work in terms of trying to make the latent space meaningful. So it's a regular GAN plus an extra term, and we could talk about how it actually works. But in terms of the latent space, this is what we see. When they B, you can ignore because that's no meaning. That's just for comparison. Things don't mean anything. But what we see is that it not only learned a representation of numbers, but there's, in the latent space, this part of the latent space changes your width. This part of the latent space changes your angle. This part of the latent space changes the whatever it is. So you're actually able to develop that understanding, and while the task you're training it on might just be generate images, now you've actually got sliders. And what they're showing is each row is a different digit, and then left to right is changing the thing. So saying this slider changes the width in D. This slider is rotation, whatever it is. And you're able to recover that information. Adversarial autoencoders, I'll have to wrap up soon in just a second, but adversarial autoencoders are also a actually, adversarial autoencoders I might cover next time because that's a bit of a cheapness. But adversarial autoencoders trying to learn that hidden representation. And the BIGAN architecture is also, I think, called adversarial feature learning, something along those lines. But we'll talk a little about these and how they try to learn a feature space. And this is the VAE versus adversarial autoencoder, and kind of the things that people see when they're doing GANs versus AEs and VAEs. Is if you try to make a VAE go into a shape, it tries to get into that shape, but it has some flexibility and it might not fit that shape exactly. Versus when you're dealing with a GAN or an adversarial autoencoder or BiGAN or any of these other GAN-based architectures, the latent space that you find is going to be like exactly the latent space you want it to be. So your images fill up the latent space much more completely, and they cover the latent space. They're not holes in the latent space. And that also means that your images that you produce don't have the blurriness that people saw when they were using VAEs. But one kind of beautiful take it home, which I'll end with, is this CycleGAN, which will hopefully express why GANs can do things that VAEs and really nothing else could do but a GAN. This is CycleGAN. It's able to convert pictures of zebras into pictures of horses and pictures of horses into pictures of zebras. And the reason this is so fascinating is because if you were trying to do this naively, what would you do? You would have paired pictures of horses and zebras in the same pose, and you would train a network to take one as the input and one as the output. And if you had a data set of horses and zebra pictures that were paired up, that would be a pretty easy problem to solve. But no one has that. That's an insane data set to collect. That's ridiculous. That makes no sense. What you can have is you have pictures of zebras and pictures of horses as just blobs, not paired up or anything. And the CycleGAN is able to actually convert from one distribution to another. It can horsify or zebrify, and yet it was never given any pairs. And that's what the power of the GAN is that you can convert from one distribution to another distribution. You can make distributions similar. You can minimize the divergence between two distributions, even if you never had any pairs. And what that's getting to is something called the optimal transport problem, which we will talk about next time as we get into Wasserstein GANs and really like what we're trying to solve here. But any questions we have as we're a few minutes over? Feel free to jump in. Otherwise, we'll continue next week. And you guys can just enjoy some beautiful photos of...
Questions, anyone? I guess not. We're kind of slightly over, so I assume that we'll be rushing off to other classes. Thanks a lot, Ben. This was fantastic. Guys, we'll pick up again over here from here on Wednesday. If you have any questions, post on Piazza. Thank you.
All right. Always open for questions. Thanks, guys. Have a great day.